1357, cyclooctatetraene, COT, is an unsaturated derivative of cyclooctane, with the formula C8H8. It is also known as 8-annulene. This polyunsaturated hydrocarbon is a colorless to light yellow flammable liquid at room temperature. Because of its stoichiometric relationship to benzene, COT has been the subject of much research and some controversy. Unlike benzene, C6H6, cyclooctatetraene, C8H8, is not aromatic, although its dianion, C8H2-8, cyclooctatetraenide, is. Its reactivity is characteristic of an ordinary polyene, i.e., it undergoes addition reactions. Benzene, by contrast, characteristically undergoes substitution reactions, not additions. History. 1357, cyclooctatetraene was initially synthesized by Richard Willstatter in Munich in 1905. Willstatter noted that the compound did not exhibit the expected aromaticity. Between 1939 and 1943, chemists throughout the U.S. unsuccessfully attempted to synthesize COT. They rationalized their lack of success with the conclusion that Willstatter had not actually synthesized the compound but instead its isomer, styrene. Willstatter responded to these reviews in his autobiography, where he noted that the American chemists were untroubled by the reduction of his cyclooctatetraene to cyclooctane, a reaction impossible for styrene. During World War II, Walter Reppe at BASF Ludwigshafen developed a simple, one-step synthesis of cyclooctatetraene from acetylene, providing material identical to that prepared by Willstatter. Any remaining doubts on the accuracy of Willstatter's original synthesis were resolved when Arthur C. Cope and co-workers at MIT reported, in 1947, a complete repetition of the Willstatter synthesis, step by step, using the originally reported techniques. They obtained the same cyclooctatetraene, and they subsequently reported modern spectral characterization of many of the intermediate products, again confirming the accuracy of Willstatter's original work. Structure and bonding. Early studies demonstrated that COT did not display the chemistry of an aromatic compound. Then, early electron diffraction experiments concluded that the C-C bond distances were identical. However, X-ray diffraction data from H.S. Kaufman demonstrated cyclooctatetraene to adopt several conformations and to contain two distinct C-C bond distances. This result indicated that COT is an annulene with fixed alternating single and double C-C bonds. In its normal state, cyclooctatetraene is non-planar and adopts a tub conformation with angles C equals C minus C equals 126.1 degree and C equals C minus H equals 117.6 degrees. The point group of cyclooctatetraene is D2D. In its planar transition state, D4H transitional state is more stable than D8H transitional state due to Jahn-Teller effect. Synthesis. Richard Willstatter's original synthesis, 4 consecutive elimination reactions on a cyclooctane framework, gives relatively low yields. Repp's synthesis of cyclooctatetraene, which involves treating acetylene at high pressure with a warm mixture of nickel cyanide and calcium carbide, was much better, with chemical yields near 90%. COT can also be prepared by photolysis of barylene, one of its structural isomers. The reaction proceeding via another isolable isomer, semibulvalene. COT derivatives can also be synthesized by way of semibulvalene intermediates. In the sequence illustrated below, octaethyl cyclooctatetraene, C8A8, is formed by thermal isomerization of octaethyl semibulvalene, itself formed by copper, I. Bromide-mediated cyclodimerization of 1234-tetraethyl-14-dilithio-13-butadiene. Because COT is unstable and easily forms explosive organic peroxides, a small amount of hydroquinone is usually added to commercially available material. Testing for peroxides is advised when using a previously opened bottle. White crystals around the neck of the bottle may be composed of the peroxide, which may explode when mechanically disturbed. Natural occurrence. Cyclooctatetraene has been isolated from certain fungi. Reactions. The pi bonds in COT react as usual for olefins, rather than as aromatic ring systems. Mono and polyepoxides can be generated by reaction of COT with peroxyacetes or with dimethyl dioxirane. Various other addition reactions are also known. Furthermore, polyacetylene can be synthesized via the ring-opening polymerization of cyclooctatetraene. COT itself, and also analogues with side chains, have been used as metal ligands and in sandwich compounds. Cyclooctatetraene also undergoes rearrangement reactions to form aromatic ring systems. For instance, oxidation with aqueous mercury. 2. Sulfate forms phenylacetaldehyde and photochemical rearrangement of its monoepoxide forms benzofuran. Cyclooctatetraenide as a ligand. COT readily reacts with potassium metal to form the salt K2COT, which contains the dianion C8H2-8. The dianion is both planar and octagonal in shape and aromatic with a Huckel electron count of 10. Cyclooctatetraene forms organometallic complexes with some metals, including yttrium and lanthanides. One-dimensional U-COT sandwiches have been described as nanowires. The sandwich compounds uranosine, U-COT, 2, and bis, cyclooctatetraene, iron, Fe, COT, 2, are known. Fe, COT, 2. When refluxed in toluene with dimethyl sulfoxide and dimethoxyethane for 5 days, is found to form magnetite and crystalline carbon, also containing carbon nanotubes. See also cyclobutadiene, pentylene, parylene, structural isomer of cyclooctatetraene, heptafulvene, structural isomer of cyclooctatetraene, semibulvalene, benzene.